How small a current can you measure in a scanning tunneling microscope, or indeed in any device? The limiting factor is this resistor in the current to voltage converter, because resistors have associated with them thermal noise owing to the equipartition theorem. So there are fluctuations both in voltage, for which the power will go as V squared over R, and fluctuations in current, for which the associated power will go as I squared R. Both of these contribute 1/2 kT from the equipartition theorem, and so therefore the power associated with noise fluctuations is on the order of kT. When one carries out this calculation in detail for a bandwidth delta F, that's a range of frequencies passed on to the control system, a factor 4 has to be put in front of this expression. The corresponding root mean square current fluctuations then from the definition of power as I squared R and Ohm's law are 4 kT delta F over R. This would appear to tell us that the best choice for this resistor is infinity ohms. However, there is a second constraint here, which is that stray capacitance associated with the input forms a low-pass filter, and this limits the bandwidth of the amplifier. It's very hard to get an input capacitance of less than about 2 picofarads. It can be done, but let's take this as a typical value. So if we have a large value of 100 megaohms, and we calculate for 2 picofarads the time constant, which is R times C seconds, and take 1 over this, we get a frequency of around about 5 kilohertz. So this is the 3 dB point, or the point where the response has fallen to half of this amplifier, just owing to stray capacitance and the finite value of the resistance R. If we now plug this back into this formula here for delta I, we would calculate then a noise threshold for current of around about 6 picoamps. One can do better than this, but at the expense of bandwidth. Let's turn to a different topic now, which is what STM images mean. So we'll talk about this in more detail in later chapters, but what I've done here is to state Fermi's golden rule. It appears in this expression where T is in effect the matrix element for electrons to have some overlap between the electrodes in the probe and the electrode on the surface. And these two terms here are the density of states of the surface and the probe. So the positively biased element, let's just draw an energy diagram here. The positively biased element will have its energy lowered by an amount E times V volts, so that the net flow of current will be from filled states in the negatively biased electrodes to empty states in the positively biased electrodes. And that's what this integral is. It's an integral over this range of energies here. It comes from the formulation of Fermi's golden rule in terms of density of states, as covered in chapter 2, and we multiply it by a transmission factor which has to do with the matrix elements. In this expression here, we have used the square root of 2me over h bar squared times the square root of the work functions, and we've taken the average work function of the two electrodes. The expression at the bottom then is the final expression for the current that flows between a probe and a surface. And what this tells us then is that we integrate the density of states of the surface between 0 and V volts above the Fermi energy. This then leads naturally to an application of scanning tunneling microscopy at higher biases, which is a way of measuring the density of electronic states around the so-called Fermi level, which is the highest occupied electronic state in a metal electrode, and we'll discuss that more in chapter 5. So the density of states can be measured simply by looking at current voltage curves versus bias. What is done to normalize this a little is to plot the current divided by voltage as a function of voltage. If you multiply by the electronic charge, you have the energy in electron volts. And so you see here that there are features in this curve that are associated with the density of states of the material. What is shown on this slide is that techniques that measure the surface density of states, for example, ultraviolet photon spectroscopy, which knocks electrons out of the occupied states with ultraviolet photons, or inverse photoemission, which measures the density of unoccupied states, show peaks in regions associated with features in this curve. And if in fact one takes, rather than I over V, this quantity, d log I over d log V, one can see more clearly features that look somehow like the sum of the ultraviolet photoelectron spectroscopy and the inverse photoemission spectrum. The point here is that these measurements are made not on a bulk surface, but on atomic features on the surface. And what the top plot shows is a spatially resolved spectroscopic map of states on the silicon 7x7. This is work of Bob Hamer's, who pioneered the atomic resolution spectroscopy of electronic states on surfaces using a scanning tunneling microscope.